How is inductive reasoning used in geometric proofs? Imagine you're looking at a pattern in shapes and wondering if it applies to all similar figures. That curiosity is the start of how inductive reasoning works in geometry. When you observe specific examples like several triangles or rectangles, you notice consistent properties. For instance, you might see that in many rectangles, the diagonals are the same length. From these observations, you form a guess that this property might be true for all rectangles. This guess is called a conjecture. It's based on patterns you've seen but isn't yet proven. Inductive reasoning is like being a detective gathering clues. You look at several cases and notice a pattern. Then you suggest that this pattern applies everywhere. But remember, just because something happens in many cases doesn't mean it always will. That's why inductive reasoning alone isn't enough to prove something. It's a way to generate ideas or hypotheses. In geometric proofs, inductive reasoning often kicks off the process. For example, you might examine a few right triangles and see that their non-right angles are always less than 90 degrees. Based on this, you might guess that all right triangles have two acute angles. To turn this guess into a proof, you need to use deductive reasoning. That means applying known facts, like the triangle sum theorem, which states that all the interior angles of a triangle add up to 180 degrees. Since a right angle is 90 degrees, the remaining two angles must add up to 90 degrees, making each less than 90 degrees. This process, using inductive reasoning to create a hypothesis and then confirming it with deductive reasoning, is how many geometric proofs are built. It helps break down complex ideas about shapes and angles into manageable steps. Inductive reasoning encourages careful observation and pattern recognition, while deductive reasoning provides the logical structure to prove the idea is true for all cases. Think of inductive reasoning as noticing clues in specific shapes, like how the diagonals of several rectangles are congruent. Deductive reasoning then takes those clues and builds a solid case, showing that the property applies universally. This combination makes geometric proofs both understandable and reliable. It's a smart way to connect what you see with what you can prove, turning simple observations into solid mathematical truths.